Hello guys, I hope you all are doing good. I am Vaishali Kikan and we are discussing the VLSI technology. Today in this video, we are going to talk about the CMOS processes. So this is the new playlist that we are going to start today, and I hope you will be staying with me till the end of this playlist and you will be understanding a lot about the CMOS processes. So we are talking about the various technology. We are going to compare the 1980s technology with the 1990s technology for the CMOS fabrication, and we are going to talk about the basic difference between the copper metallization and the traditional metallization. So if you have still not watched the previous playlist where I talked about the process integration and the various processes required for the formation of an IC, it is highly recommended that you go back, watch that playlist first and then come to this video. I hope you understand all of the processes before you are coming to this video, because I'm not going to again talk about all of the processes in detail in this video. So let's talk about the introduction to the CMOS fabrication process and the 1980s technology. It is a very basic technology, and we are going to see the difference between 1980s technology and the other technology as well. So the objectives of this playlist is to list the major process technology changes from the 1980s to the 1990s. Then we are going to talk about the 2000s technology as well, and then we are going to explain the basic difference between the copper metallization and the traditional metallization. I had already talked about this basic difference in the copper interconnection formation video as well. I hope you all have seen that. Now we are going to analyze in detail how these two are different for the CMOS fabrication process as well. So now how the technology was changing from 1960 to 1970, let's observe it. So in the 1960s we were making the PMOS ICs, right? So only the PMOS ICs were there. How we were making the PMOS ICs? With the help of diffusion, and there I was using the metal gates, right? So in the 1970s, as the polysilicon gate were developed, right, we had the polysilicon gate which were having the higher temperature tolerance. It was not melting at a higher temperature, unlike the metal gate. The metal gate will be melting at a higher temperature, but the polysilicon gate will not. So this is an additional advantage, and due to which I can use the ion implantation, and with the help of ion implantation I can fabricate NMOS as well. So in the 1970s we moved towards the NMOS technology. NMOS technology was giving me the faster products, right? So this was a very big advantage over the PMOS products. So now coming to the 1980s technology. So here in the 1980s, LCD replacing LEDs as indicators for the electronic watches and the calculators, right? So this was a very big change in the 1980s. We were having the LCDs which were replacing the LEDs as the indicators. So now in the IC also, the CMOS IC was replacing the NMOS IC for the lower power consumption, right? If I was using the CMOS, it was having one additional advantage. Okay, the speed was high, but there is an additional advantage of having the lower power consumption. And also the minimum feature size was reduced from 3 micrometer to 0.8 micrometer. The wafer size was increased from 100 mm, that is 4 inch, to 6 inch, that is 150 mm. So these are all the changes that we were having in the 1980s. So in the 1980s CMOS technology, we were using the local oxidation of the silicon. We were using the phosphosilicate glass and the reflow of the phosphosilicate glass for the planarization. After that I was using the evaporator for the metal deposition. We were using the positive photoresist. Projection printer was used. After that we were using the plasma etching as well as the wet etching. So you can see, first of all, we can do the wafer cleaning. We have the P type of substrate and we can do the wafer cleaning with the RCA technique. After that we will be having the pad oxidation, right? Pad oxidation is a very thin layer of the oxide. So after that we can have the LPCVD of the nitride layer. This is the low pressure chemical vapor deposition of the nitride. This is how I can form the silicon nitride layer over a very thin pad oxide layer. Right, after that we will be having the photoresist coating. Okay, over the silicon nitride I will be having the photoresist layer. right? After that we can use the mask 1, which is used for the local oxidation of the silicon. So this is my mask 1, which is used for the local oxidation of the silicon, right? I hope you know the functioning of the local oxidation of the silicon, why it is used, right? I hope you understand it. If you are not able to recall its functioning, you can go to the previous playlist. After that we will be doing the alignment and the exposure, so that the photoresist over here will be having the change in its characteristics, right? After that we will be going towards the development phase, so that the changed photoresist is going to remove with the development solution. Right here we have made a mask now with the help of the photoresist. After that we can have the etching cycle, where I am going to etch out the nitride layer. Okay, here I have etched out the nitride layer. After that we can strip off the photoresist, it is no longer required, so I can strip off. Then we can have the isolation implantation. We can have the isolation implantation with the help of the boron atoms. Okay, so we will be having the boron ions which are moving here, and it is forming the isolation with the help of the P type of ions, that is the boron ions. If they are in higher concentration in the P type of substrate, it is going to form the isolation. This is called the isolation implantation. After that we will be doing the local oxidation of the silicon, and with the help of oxidation cycle. Okay, here I will be having the oxygen atoms which are forming the SiO2 over here, right? So here you can see we have formed the SiO2. After that we are going to strip off the nitride as well as the pad oxide, and then I am going to clean it, right? So now here you can see we have the isolation formation, SiO2 isolation formation. Here we have the isolation implantation as well. Now we can move towards the next processes. Okay, so first of all we are going to make a screen oxidation layer. Again I am going to give some oxygen atoms, and the oxygen atoms will be going and reacting with the substrate over here. It is going to form a very thin screen oxidation layer. After that it is going to have a photoresist coating cycle, where we are going to coat it with the photoresist over here, right? After that we will be using the mask 2 for the N-well formation. First of all I have to form the N-well in the P type of substrate. So this is the mask for the N-well, and here you can see we can change the characteristics of the photoresist over here with the help of the exposure and the development phase. This was the alignment phase, where I was aligning this mask with the given wafer in a perfect manner, so that it will be placed at the perfect location where I want the N-well, right? So after that I will be going through the exposure phase, where I will be changing the characteristics of the photoresist while exposing it with the UV light. Okay, here the UV light is not going to penetrate this mask, and this is how here the characteristics of the photoresist are not going to change. After that I will be going through the development phase, where I will be making the mask in the photoresist over here. And after that I will be doing the N-well implantation with the help of the phosphorus ions, and here you can see here we have formed the N-well, right? So after that we are going to strip off the photoresist, it is no longer required, and then I will be doing the N-well drive-in and the annealing as well, so that the depth and the width of the N-well is going to increase, right? So you can see it here, the depth was not much, and here after drive-in phase, which is a high temperature process, and the annealing process, which is again a high temperature process, the phosphorus ions are going to penetrate deep inside the P type of substrate, and this is how it is going to form the N-well. After that we are going to strip off the screen oxide, it is no longer needed. So you can see here we have stripped off the screen oxide. After that we are going to grow the sacrificial oxide. Sacrificial oxide and the screen oxide are having the different width. I hope you understand it. I told you about the various oxide layers and their importance and their thickness in the previous video, where I talked about the oxidation of the silicon, right? So now here I have grown a thin layer of the sacrificial oxide layer. Okay, then I will be stripping off the sacrificial oxide, right, so that I will not be having any contaminant particles over here. The contaminant particles will be now removed, right? After that we are going to grow the gate oxide, right? So first of all we will be having the gate oxide over here, and after that we are going to deposit the polysilicon. So now this is the polysilicon layer that we have. This is the auto aligned process that we have. We don't need to have the alignment afterwards. We are doing the self alignment. For that, first of all, I am making the gate and then I will be doing the doping, right? So here we have made the polysilicon layer for the gate formation. Right, so after that we can do the photoresist coating, and you can see here we have the photoresist over here, and after that we will be having the third mask for the gate and the local interconnection, right? So this is the mask that we are using, and here we are using this mask, and here we are exposing it. First of all, we are having the alignment phase. We have aligned the mask over here. After that we have the exposure phase, where we have exposed it with the UV light, and after that we are going to the development phase, where we have removed the changed characteristics of the photoresist over here, right? After that we are going to etch out the polysilicon, right? Over here we don't want the polysilicon, so I have etched out the polysilicon layer over here, right? So here we have the photoresist layer, below that we have the polysilicon, and then we have the gate oxide layer. But here at this point, this point, this point and this point, I won't be having the photoresist and the polysilicon layer, right? So this is how I have made the mask. The photoresist is now no longer required. It has served its purpose, so I can strip off the photoresist now, and again I can do the photoresist coating. So you can see this is the photoresist over here, and inside here we have the polysilicon over here. Okay, so you can see now I am using another mask for N type of source and drain formation. You can see we are using the mask over here so that I will be having the N type of source and drain formed inside the P type of substrate. Right, so you can see we will be going to the exposure phase, where I am going to change the characteristics of the photoresist. After the alignment phase, the exposure phase is there. After that we will be having the development phase, where I have removed the photoresist, and after that I will be having the P implantation, where I will be going to implant the P type of substrate with the help of the N type of materials. This is a phosphorus implantation that we have, and this is how we will be having the N type of regions over here, which is going to form the N source and the N drain. So you can see here, after that the photoresist is no longer required. We can strip off the photoresist. After that again we are going to do the photoresist coating, because the photoresist over here was having the mask over here. So this mask is no longer required. This mask has already served its purpose. So now again we are moving towards the photoresist coating cycle. So first of all I will be stripping off the photoresist, then I will be again coating the photoresist layer, and then I will be using the mask 5 for P type of source and drain exposure. So first of all I have aligned the mask. The P type of source and drain exposure mask is aligned now, and then it is exposed to the UV light, and this is how the characteristic of the photoresist has changed over here. And after that we can go to the development phase and remove the photoresist, and then I can go to the ion implantation with the help of boron ions, and this is how we will be having the boron implantation, and this is how we will be having P plus region in the N well. So after that the photoresist is no longer required. We can strip off the photoresist, and then we can do the annealing. With the help of annealing we can have the higher width or higher depth of the N type of source and drain as well as P type of source and drain. So the depth will be increasing with the annealing process. After that we will be doing the LPCVD of the barrier nitride, right? The low pressure chemical vapor deposition of the barrier nitride layer, and after that we will be using the CVD chemical vapor deposition of the borophosphosilicate glass. Right, after that we will be using the high temperature to reflow the borophosphosilicate glass, because here you can see the roughness was very high. To make it smooth I will be using the high temperature, in which the borophosphosilicate glass is going to smoothen out like this, right? So this is called the BPSG reflow. After that again I am going to do the photoresist coating. You can see over here we have the photoresist coating, and after that we are going to use the mask 6 alignment for the contact exposure, right? So here I will be using the UV light to again change the characteristics of the photoresist, and then I will be going to the development phase. Again in the development phase I will be removing the photoresist whose characteristics are changed, and then I am going to etch out the borophosphosilicate glass as well as the nitride layer to make the contact with the source and the drain. So you can see with the help of source and drain, I have made the mask, right? So the trenches are here above the source and drain. Now I am going to strip off the photoresist. The purpose of the photoresist is again served out here, and now I am going to do the metal deposition. So you can see here, this source and drain is shorted out. Again it is shorted out with this source and drain. So this is not required. For that I will be again doing the photoresist coating, and then I will be using the mask 7 for metal interconnection exposure. And you can see over here we have changed the characteristics over the photoresist, and after that I will be going to the development phase, and here I will be etching out the aluminium copper silicon layer over this area only, right? So here you can see we are going to etch out the metal over here, and after that we are going to strip off the photoresist. And this is how I have removed the shorting out of this N source and drain, as well as this P and P source and drain. So these are now not shorted out. After that we can do the chemical vapor deposition of the undoped silicate glass. After that we can do the chemical vapor deposition of the nitride for the passivation layer. So this is how we can form the CMOS in the 1980s. So these are the references which are really amazing books which you can refer for your further studies. I hope you like this session, and if you have any further doubt, you can put the doubt in the comment. If you like it, please push the like button, subscribe to the channel, and also share it with your friends and give me your valuable feedback. Thank you so much.